In this video, we're going to learn how to sketch the respective graphs when a ball is dropped from your hand and then it goes all the way down, hits the floor, and then rebounds back to its original height. Of course, we are assuming a very ideal situation where there's no air resistance, there's no energy lost through heat and sound or whatever. Now let's analyze the motion. At position A, that is the point where you release the ball. Because the initial direction of the ball is going down, I will fix going downwards as positive. So as the ball goes down, and because you release from rest, the initial speed is 0, so it will go faster and faster because acceleration due to gravity will be 10 meters per second square. Meaning to say every second the speed actually increases by 10 meters per second. So when it hits the floor, momentarily it will go to 0 at position B, and then when it rebounds back, take note of that, when it rebounds back like an elastic ball, the speed will be the highest when it leaves the floor, and then as it goes up, it will get slower and slower because the weight, which is downwards, is opposite to the motion, causing it to decelerate, and then it reaches the highest height at point C, which is the same as A. Now let's take a look at the velocity time, and let's recall the gradient will represent the acceleration, and it will be a constant 10 meters per second square acceleration due to gravity. So at point A, where you first release the ball, the speed is 0, so I'll start from the origin, and then it will undergo constant acceleration until at point B, just before it reaches the floor, it will have the maximum highest speed. Okay, the maximum velocity, and when it hits the floor, immediately it will go to 0, and then it will rebounds back, and when it rebounds going upwards, the speed will be the maximum before it starts to slow down towards point C. So this will be a negative maximum speed or velocity. So as it goes up, the velocity will get less and less negative, and until at point C where it reaches its maximum height and the speed will be 0. So that's how you draw the velocity time graph. As for displacement time, let's recall the gradient represents the velocity, and then we have mentioned in the previous video, displacement is like the distance between the ball and the reference point, and now the reference point is at the starting point, which is at position A. So as the ball falls, the displacement between the reference point and the ball will keep on increasing. So I'll start from the origin, because at the beginning the ball is at its reference point, no displacement. So as it falls, the speed is increasing, so the gradient is increasing, it's getting steeper and steeper. So this is what you get here until point B, and here the starting point is A. And as it rebounds back, the displacement between the ball and the reference point A is getting shorter and shorter because it's going back to its original position. So the distance should be smaller, and because as it goes up, the speed is decreasing, the gradient will be decreasing, so it's getting less and less steep, and the displacement is getting smaller and smaller until point C where the displacement is 0. That means it has returned back to its original position and there's no displacement at all because it's back to its reference point. To sketch the acceleration time graph, let's take a look at the velocity time. As you know, the gradient represents the acceleration, and the gradient is a constant value, and the value is 10. So there will be 10 here, and since it's a constant acceleration due to free fall, the value is always 10. Therefore, it's a horizontal line on the acceleration time graph. Lastly, let's also take a look at the speed time and the distance time, where both are scalar quantity. So same thing, there will not be negative portion of the graph. So you start from releasing the ball from rest, you start from the origin. So the first part will look the same from A to B. Then there's a part at point B where it hits the floor, it immediately goes to 0, and then it rebounds back, and then from there the speed is decreasing until point C. So this is how it looks like. And as for distance, so the initial part is the same, so the ball goes down, the distance between the ball and the reference point keep on increasing, as you can see here, until point B. Now But because it's distant, you don't care about direction. As the ball rebounds back from B to C, it continues to cover more distance, and then you just flip the graph over, and it's getting slower and slower, the gradient getting less and less steep. So this is point C. So this is how you draw the distance time graph. One last thing that I want you to take note is the area underneath the graph of a velocity time or speed time. And the area underneath the graph represent the distance traveled. So that means to say that if this A to B, the height is 2 meters, so from B to C that will be 2 meters. So how is it represented on the velocity time or speed time curve? So this area over here, which is the same here, that will represent the distance covered. So this is like the height. You want to find the height that you release the ball, that will be the area, that will be the distance. And then for this portion B to C, that will be this area here and this area here. So if I were to ask you to find the total distance traveled by the ball, it will be from A to B, that's 2 meter plus another 2 meter, and that will be the total area over here. So in other words, this will be a total of 4 meters for this distance time curve, and at this midpoint here, there will be 2 meters. But if I were to ask you to find the displacement of the ball, okay, because it goes back to its original position, there's no distance, no displacement between the ball and the starting point. So the displacement at point C, that's why it's a 0. And point B, this will be just 2 meters over here. So I hope this video will give you a clearer picture how to sketch and how to interpret the graphs.